What do we mean by photodiode? Any idea you have regarding a photodiode? See, same PN junction, if you observe, depending on the different sort of fabrication, this can be used as diode, ordinary diode. I mean, okay. The second one is you might have already come across the another diode called as Zener Diode. Can anyone of you tell me the application of this one, Zener Diode?
The voltage regulator.
Yeah, voltage regulator. Very good. Okay, so voltage regulator. There we find this Zener diode as an application. Apart from that, have you come across any other type of diode? This whatever we are discussing. Apart from this, there are plenty of diodes in the literature. If you find it, like Schottky diode. Have you heard about it? Have you come across Schottky diode?
Just heard about it.
You heard about it, okay. The main property of this is it is not a PN junction, instead it is a metal and semiconductor diode. One of this region will be the metal, other will be the semiconductor. In these type of diode or Zener diode, both you find as a semiconductor, but in Schottky diode, it's a metal semiconductor diode. That's the only difference between that. Next, what we are discussing is going to be the photodiode. Okay, what is so special about photodiode? In today's class, we will describe each one of them, and accordingly, depending on the type of diode, the symbolic representation also keep changing. The same PN junction is also serving as ordinary PN junction, Zener diode. In all these things, doping is not uniform. It varies depending on the application. Now, let us see what do we mean by photodiode. So, photodiode is nothing but it is an ordinary PN junction diode. Okay, it has got P type and N type semiconductor regions, and it responds to the photon absorption. See, this is the property which is important for us. So, whenever you make the light to fall on this, photons are made to fall on the PN junction surface. The photons absorption is going to be responded by this. It absorbs the photons and it produces equivalent electron hole pairs. Okay, so that's why it is called as the photodiode. It responds to the photons. It absorbs the photon, and within that you are going to see electron hole pairs generated. So basically, it is a two-terminal device. As you are seeing, the symbolic representation is as shown here, which is an anode we have, and there is a cathode here. Okay, so the two-terminal device which responds basically to the photons. Okay, it converts light energy into electrical current here basically. Okay, so light energy, whichever the photon we are providing here, that in turn is converted into the electrical current. We will see how this provides electrical current from the light source. So now to start with, let us consider normal PN junction diode. For a reference here, we will take normal PN junction diode instead of going straight away into the photodiode. What you are seeing here, let us take normal PN junction diode. And here for this normal PN junction diode, you can see that the reference voltage what we have taken is VD here, diode voltage, and current flowing because of VD is ID here. So these are the reference voltages, and this is normal PN junction diode. Okay, we have considered to explain you what do we mean by photodiode, and the diode current equation which follows this. Okay, whether it is forward bias or reverse bias, the same equation is valid. ID is equal to I naught into e to the power of VD by VT minus 1. VT stands for thermal voltage, which is nothing but KT by Q. Okay, so shortly we have written as VT. VT stands here thermal voltage. Okay, so VD by VT minus 1. This is the diode current equation, which relates this voltage VD here, and it relates the current here in this way. Okay, so this is called as diode current equation. And if you observe diode characteristics here, so we have forward bias in the first quadrant and reverse bias in the third quadrant. So you can see here the reverse saturation current I naught flows here, which is a constant current which doesn't depend on this reverse voltage. Okay, so it constant small amount of current keeps flowing due to the minority carriers. Now let us see, we will consider some point here which is marked here. You can see here, say reverse voltage is minus VR. At this reverse voltage, okay, so if you apply the photons on the diode surface, let us see what is going to happen. Okay, first of all, you must reverse bias this, and in the reverse bias you must apply the photons on the top of the diode. When there is no incident light, you can see that the photodiode of it responds here, a constant current. It is just like ordinary reverse biased diode, but in the photodiode, if you specifically apply photons on the reverse bias, so then it leads it generates the further current which is beyond this current here, I naught here. So it keeps adding the value to the I naught here. Okay, that's the speciality of photodiode. And if you see the energy band diagram of the photodiode, so which is totally different from ordinary p-n junction diode. Okay, so ordinary p-n junction diode, you have seen normal Fermi levels has been broken in the reverse bias, we can see here, and this is the barrier potential. Barrier potential value is Q times V naught plus VR. Okay, so this is the amount of barrier potential we have in reverse bias, and this is the P region, you can see here P region, and here we have N region here. So this is the many things is shown here. So try to understand one by one. So this is the energy band diagram first of all for the p-n junction under reverse bias. We can see barrier potential is Q times V naught plus VR. Under equilibrium we already know, so it is just a Q times V naught. But now due to the reverse bias, it is this reverse voltage also gets added here. So barrier height has been increased here. So therefore the Q times V naught plus VR is the barrier potential here. Okay, so, and you can see the electric field is acting between from N side to the P side. This is the direction of electric field, okay, which is acting on the depletion region. Okay, so here three different processes will happen within the depletion region. This is the depletion region which has been shown here with the dotted line for a p-n junction. This is on N side, this is the depletion region. Okay, so you can see here the energy band diagram, there is no slope here, so therefore there is no electric field in the neutral P region. Slope is equal to 0, whereas in the depletion region you can see that slope is negative. Okay, you can see that it is decreasing energy level here, so therefore slope is negative, and electric field is acting in the negative x direction. Negative field means negative x means it is from N to P, we have considered as a negative x direction here. So electric field is acting from N side to P side, that is taken as negative x direction. And even in the neutral N region you can observe there is no slope, slope is equal to 0, and also the electric field is 0. So both the parameters are 0 here, slope and electric field. The same situation whatever you have seen in the neutral P region here. Okay, so now we will see here when the light is incident on this. Okay, I need not explain, Fermi level is already splitted here because of reverse bias. You can see that this is the Fermi level on the P side, and this is going to be the Fermi level on the N side, and there is a strong electric field in the negative x direction in the depletion region here. Okay, and bands have been bended in the depletion region because of the reverse bias here. Okay, now we can see here what happens when the electron hole pairs are created. See, these electron hole pairs are created due to the photons, okay, incident on this junction surface here. When the photons are incident on the onto this depletion region here, it forms electron hole pair. You can see here there is a hole here and there is an electron here. Okay, it forms electron hole pair here. Okay, so these electrons now, okay, formed due to the incident the photon on the depletion region. Now the field is so strong that it pushes electron into the N region and hole into the P region here. So this is a way the electric field will drift the charge carriers. Okay, so into the N region and P region. Electron moves to N region and hole moves to the P region here. Okay, so this is what you are seeing in the energy band diagram due to the incident light, which is H into mu. And here this incident light must be greater than band gap energy Eg. Okay, if you apply this much the photons, then definitely it can create electron hole pairs whatever you are seeing here, and these electrons are taken care by the electric field. It pushes electrons to the N side and holes to the P side here. Okay, and we have seen already, even if electron hole pairs formation takes place here, what is going to happen? Suppose if there is a electron here in the conduction band and a hole here in the valence band, so in the neutral the P region, what is going to happen? So here the diffusion process itself will push this carrier here. Suppose if electron comes here due to the diffusion process, and this is in turn will be pushed into the N region. Okay, and hole will be, again field is acting from N to P, therefore this hole will be pushed back into the neutral P region itself. Even though if hole comes near to the depletion region, this electric field is acting from N to P, therefore, this hole is pushed back into the P region itself. Same scenario happens in neutral N region also. Suppose if electron hole pairs are created here, suppose if there is an electron here and there is a hole here, this is what is going to happen for these charge carriers, electron hole pairs generated here. Same situation here also, due to the diffusion process, by chance any this electron moves close to the depletion region here, then if this hole also moves to the depletion region here, then automatically this electric field is so strong that it pushes back this electron to the N region, because the field is acting from N to P. So, it pushes the electron back to the N region, and hole here will be pushed back to the P region here. So, this whole particular hole get pushed back to the P region here. So, this is how the charge transport mechanism happens within the PN junction here. Okay. We have seen 3 different layers here. What happens to the electron hole pairs here, and in neutral P and neutral N region here. Okay. Now, let us assume that light is coming from one side, as you are seeing, observing here. This is the light energy is taken as H into mu, if that should be greater than Eg, to excite electron from the valence band to the conduction band. Okay. So, this is the amount of energy, photon energy required to excite electron from the valence band to the conduction band. By this, the electron hole pairs are generated. Once electron hole pairs are generated, this entire process is split into 2. One is carrier generation, other one is carrier transport or carrier multiplication, what we call. Okay. So, this carrier generation creates electron hole pairs, and the carrier transport mechanisms, that is electrons and holes, are sent to the N region and P region respectively due to the strong electric field in the depletion region here. Okay. So, EHP in the neutral region already we explained here what happens, because due to the here diffusion process will play here, and due to that, if any electrons are comes near to the depletion region, and the field will take care, and it causes electron to push to N, holes to the P side here. So, there is no transport carrier, carrier transport mechanism happens in the neutral region, because of there is no electric field in the neutral region. Only thing is diffusion process should happen there. Okay. Now, let us see here what happens if you observe the characteristics. Earlier we have seen only diode characteristics here, which has got forward bias and reverse bias here. So, this current we called as dark current, because here even though you apply reverse voltage here, the light photons are not incident. So, due to that small amount of reverse current flows here. And further, if you increase the photon, what happens? So, as we have said already here, when you increase the photons, so obviously more and more electron hole pairs are generated, and more electrons get collected in the N region, more holes get collected on the P region, and that creates more current. You can see here, this is due to the intensity 1, this is the amount of magnitude of current flowing, and due to the intensity 2, let us say large photons are injected. So, this is the amount of current flowing here. Okay. So, this region, if you observe here, this region is nothing but it is a region of operation of photodetector here. So, whether depending on the intensity current here, we can say whether what quantity of photons are injected here. So, that is why the region quadrant 3 will act like a photodetector here, whereas the quadrant 4 will act like a energy generation, which is nothing but the solar power. We can do that by calculating this V into I product also. Okay. So, you can compare that with the product of this can be compared. You can see that when Vi product is positive, you can see that it will act like a passive, it consumes energy. Here also you can see that voltage is negative, current is also negative, the Vi product is positive. So, therefore, here also the device act like a passive device, whereas in fourth quadrant, if you observe, voltage is positive, current is negative, but Vi product is negative. Okay. So, therefore, Vi product is negative, this acts like a source of energy, it is not like a the consumption of energy, it generates energy here. So, therefore, it supplies power to the circuit here. Therefore, solar cells are operated here. So, photovoltaic or solar cell is operated in the fourth quadrant here. So, those who want to understand about solar cell, so you need to be familiar with these voltages like VOC and ISC. These are the extreme limits of the voltages, okay, wherein which you can operate the solar cell. So, maximum voltage you can operate is this, and current is this. So, the voltage and current product should not exceed this VOC into ISC. Okay. Now, let us see the other points here. Compare with and without incident light on PN junction. Without light, we have already seen dark current flows, no incident light. So, there is I naught is flowing. This is due to the reverse saturation current due to the minority carriers. With incident light, more electron hole pairs are generated, so amount of carriers is more, so it does not depend on the potential applied, even though whatever potential applied does not depend, and the current keeps increases because of the electron hole, more and more electron hole pairs are generated. So, what will happen to the current when the voltage applied is 0? Okay, when voltage applied is going to be 0, so let us see what happens here. Okay, so this is the condition, circuit condition when voltage applied is 0, Vd is made 0, you can see here, and this condition we already discussed when the voltage applied is reverse bias, and you can see here the current now when the light is incident on this, then definitely the more and more current keeps flowing without reverse, without the photons. We have already seen this is the amount of current flows. With photons on this, current keeps increasing. Okay, this condition we have already seen. So, Vd is equal to minus Vr in this case, voltage across the photodiode, and the current here already we have a reverse saturation current I naught, and for this the current due to the photons, which is called as IL. Okay, this is nothing but a diode current which is due to the light, let us say IL, and now these two currents will get added up. So, total current flowing due to the incident light is now this. Okay, so, ID is equal to I naught minus I naught minus IL. I naught is nothing but which is the reverse saturation current, this is the minus IL is nothing but which is the same direction, of course, you can see the direction of the current here. So, I naught is reverse saturation current, IL is the current due to the photons, and both are in same direction, so that will get added up. So, current enters through the higher potential here, this topic will take up later. So, this is the total current flowing when the photodiode, okay, when the photons are made to fall on the diode here. Now, here we will discuss what happens to the current, whether current flows or not when the voltage across the photodiode is made 0. Now, let us see here what happens for this. So, you can see the condition here, voltage, how do you make voltage as 0? We need to short circuit it. So, we have short circuited the photodiode, and now see, let us see, if you observe energy band diagram, if you make the photons to fall on this, what will happen? Again, if you have to look at the energy band diagram, there is no voltage applied across the diode, but only thing is we are injecting photons here. These photons already we know that if the energy h into mu, if it is greater than Eg, then definitely it can create electron hole pairs. As you are seeing here, this electron hole pairs are created even though without applying any voltage, and more incident light if you apply on this, more and more electron hole pairs are created here. Okay, already the field exists between N and P. So, this field here it will drive the electron to the N side and holes to the P side here. Still there is a movement of charge carriers, as you can see here. Okay, so it causes current. Now, current through the diode is not 0. Okay, it is negative. Okay, you understood this one? So, even though if you make voltage as 0, but still if you incident light on this, on the photodiode, still it can create electron hole pairs. So, electrons are moving up, and corresponding holes are down here. The electric field will take care of movement of charge carriers, that is electrons to the N side is pushed and holes are pushed into the P side here. So, therefore, all electron keep moving this side from a depletion region to the N side, holes keeping from moving from depletion region to the P side, and therefore, some carrier transport mechanism happens here that leads to the current due to the incident light here. So, this is under no bias condition here. So, current is not 0 here. Okay. And here when it comes to the fourth quadrant here, as I told you already, fourth quadrant is nothing but it is a region of operation of solar cell, because Vi product is going to be negative. To explain that we have taken this the two separate circuits here. Suppose if you observe the resistor, okay, through the resistor current flows from higher potential to the lower potential. So, therefore, the Va product of this current flowing through this and the resistance of this, if you take up these two, it is not resistance, it has got some resistance here, and the current flowing through this and voltage across this, if you take out Va product of this, usually it will be positive here for the resistance material. Okay. Whereas, in the power supply, as you can see here, current leaves the positive terminal and enters the negative terminal here. Okay. So, this kind of situation, power supply, if you observe here, the Va product of this power supply is going to be negative. That means, any system with Va product as negative, it supplies the power. Any system with Va product as positive, it consumes the power. So, to illustrate the these two concepts here, these two examples have been taken here. Basically, resistor is a passive device, and the VA product of the resistance is always positive, because current enters the higher potential and leaves the lower potential. The VA product of this across the resistor is going to be always positive. Whenever you get VA product as a positive quantity, you can think of it as a energy consumer, it is not a energy supplier. Whereas, in case of the power supply, a battery like this, current leaves this positive terminal and enters the negative terminal here, and if you take out the V and I product here, it is a negative quantity here. So, whenever you get VI quantity as negative, that means the system supplies the power to the external to other circuit here. Okay. So, this mechanism, this concept is applied even here also. So, we have seen already here VI product is positive in the first quadrant, here diode is consuming power, and even in third quadrant you can see that we told this is a region of operation of photodetector. Okay. Here also PN junction consumes power because VA product is positive, whereas here if you can make an observation, voltage is positive, current is negative, therefore, VA product is negative. Okay. So, as we said already, whenever we get VA product as negative, it is a supply or a supplier of power. So, therefore, in this region a junction designed properly can operate like it can work like a solar cell. Okay. Okay, so that is what we want to say here. In fourth quadrant VA product is negative. So, it supplies the power to the external circuit. So, it converts light energy into the electrical energy here. Okay. So, this is what we want to say in a with reference to a solar cell. So, now if you calculate VOC and ISC, VOC and ISC we already seen, these are the extreme limits. This is the one of the higher limit is VOC and lower limit is ISC. To calculate that, we can use this circuit mechanism here. So, VOC means it is a open circuit across this. Okay. So, we are not going to provide, we are not going to do short circuit here. Intensity is going to be 0 and voltage across the diode is also going to be 0. When intensity is not equal to 0, what happens here? So, when the VD is going to be positive here. Okay. So, whereas in the short circuit condition, you can see observe here. So, when you make in the intensity as 0, the current is also going to become 0. When the photons are not, when the photons you are injecting here, when intensity is not equal to 0, when the light photon energy is made to fall on this, then the current here, the diode current will become equal to ISC, which is also equal to the minus IL. Okay. So, this is what the conditions you need to aware for open circuit and short circuit conditions. Okay. Coming to the PN junction here as a solar cell. Okay. So, this is again specially designed the diode PN junction. It looks like ordinary diode only, even if you take solar cell and observe it, it is nothing other than the PN junction. Okay. But it is specially designed, that is all. And the structure of a solar cell, if you look at here, okay, it resembles like this. As you are seeing here, there is an N layer, thin N layer here, and there is a thick the P region here, and there is a junction what you can observe here. Okay, between the N and P there is a junction here. This is the structure of a solar cell, and there are metal contacts which are in the form of a finger fashion. You can observe here. These are the metal contacts here. Okay. And if you observe this in 3D, it looks very good. As you are seeing here in the bottom, you can see that top view of this or three-dimensional view of the solar cell. Okay. So, and adjacent to this we see this there is a reflection, anti-reflection coating, so that whenever the light is made to fall on this, light should not reflect away. Therefore, the anti-reflection coating is made on the top of this surface. So, the light exactly falls on this the N type, and this is made so thin, so that directly photon energy enters into the junction here. So, here the electron hole pairs are generated, and that it results in a current flow from N side to the P side here. And this is of course the base contact layer. You can see that the bottom here, which is a metal contact, what you can see here. Okay. So, this solar cell you must operate within this limit here, as you are shown the region of operation here. This VOC and ISC is the region of operation of solar cell here. Okay. Within this region, okay, you can extract maximum energy from the solar cell. That means maximum energy in a sense you can obtain maximum current from the solar cell if you operate within this region of operation. Okay. With that, let me move on to the equivalent circuit representation and energy band diagram we have already seen here. So, once again I reiterate for solar cell it is not at all different from ordinary photodiode, it is almost same. when the light is made to fall on this the solar cell, what is going to happen? And again see, it creates electron hole pairs, and field is already exists in the equilibrium. That field moves electron to the n side, holes to the p side, and it results in a current called as light current IL that flows from n side to the p side here. So, this is the direction of current IL flowing from n side to p side due to the incident light H into mu. Okay. So, electrons electric field exists from n to p, and there is a current movement also from n to p side here. Okay. So, this is the energy band diagram of the solar cell. And now, let us write the equivalent circuit of the solar cell, and later on we will explain the mechanism, okay, how we can extract maximum energy from the solar cell. So, this is a solar cell symbolic representation, that is a diode. It is nothing but diode with this arrow mark representation that shows solar cell. In order to draw an equivalent circuit, what we do is, we will since if you see this solar cell, okay, first of all you can write this as you can write this with without this arrow mark. If you treat this as an ordinary junction diode, we can represent with this symbol, this ordinary junction diode. The main distinction between ordinary diode and the photodiode is, whenever light falls on this, it generates current. Okay, so it generates current here. So, the current generation is taken as current source here. Okay, so this is nothing but IL, and we know that current flows from n side to p side here. Okay, understood this here? So, ordinary diode, this is normal PN junction diode with current source parallel to this together total represents this photodiode or solar cell. Okay. So, the current flowing through the ordinary junction diode, we are already aware of it, I naught into e to the power of Vd by Vt minus 1. Okay, so, Vd is nothing but voltage across this e to the power of Vd by Vt. Vt already we said it is a thermal voltage, Vd minus 1. So, this is normal PN junction diode. Parallel to this, if you connect a current source here, why we have connected a current source here? Because in the absence of light, okay, this photodiode behaves like an ordinary diode. Okay. Because of this, the extra light, whenever you light, photons is made to fall on this behaves like a current source here. So, therefore, for ordinary PN junction diode, if you include a current source parallel to the diode here, connected current source from n side to the p side, if this current flows from n side to p side, this total circuit is nothing but an equivalent circuit of the solar cell. Okay. So, this is an equivalent circuit of this. Now, let us take total current flowing through the solar cell. You can see here the current ID due to the diode behavior, it is from flowing because of this Vd, it is nothing but ID which is flowing, and due to the incident light, this IL is flowing, both are going to be opposite in direction. So, therefore, total current here is nothing but I naught into e to the power of Vd by Vt minus 1 minus IL, if you call this as equation 1. Now, we can obtain these extreme limits, already we have discussed here VOC and to VOC and ISC. So, do we do that? So, you can see here now. So, you can see here now we have taken total current equation here. In this equation, VOC can be estimated by making ID as 0. I already told you why do you want to make ID as 0, because here to estimate VOC, the current will be typically 0 here. So, this is on the x axis, therefore, ID is going to be 0 here. So, when ID is equal to 0, this VOC is nothing but equal to Vd only. Okay. So, Vd is nothing but it is a diode voltage. So, therefore, in this equation what you can see here is VOC is equal to Vd under the condition ID is equal to 0. Now, substitute here in place of Vd as VOC, and you can make ID as 0. This is what we have done, simplification you can see here. So, if you do that, so on simplification you can see that you can transfer IL to the left hand side, IL plus IL divided by I naught plus 1 is equal to e to the power of VOC by Vt. Or you can take this, we want VOC here. So, VOC open circuit voltage is nothing but Vt ln of IL by I naught plus 1. So, this is called as open circuit voltage. So, maximum voltage so you can operate the solar cell is VOC. Okay. And let us find the short circuit current here. Short circuit current is this. To obtain the short circuit current here, you must make Vd as 0 here. So, here if you make Vd as 0, the current that is flowing ID will be equal to ISC. Okay. So, let us see here how do we get it that. So, ID, okay, so ISC will be equal to ID under the condition Vd is equal to 0. The same equation, equation 1, if you substitute as Id as Isc and if you make Vd as a 0, if you make Vd as 0 here, you can see that the complete e to the power of 0, this becomes 1 here, 1 minus 1 cancels out here, and you are left out with minus IL. So, Id will be equal to minus IL, that can be called as short circuit current here. So, short circuit current is equal to minus IL here. So, we came to know that these two quantities here, VOC and ISC, there is a region of operation of solar cell. It is a maximum voltage and current wherein which you can use to extract maximum energy from the solar cell. Now, we can see here how do we get the efficiency of this. So, now if you, for the simplicity, what we are doing here is this curve what you are seeing here in the fourth quadrant, we will just flip it to the first quadrant and see the how can we utilize extract maximum energy from the solar cell. How do we flip this into the first quadrant here? We want this what you are seeing here, we want here. So, to do that you just make current as absolute value or positive value. If you do that, this kind of characteristics you are going to get it here, and VOC is nothing but maximum voltage, what you are seeing here, ISC is nothing but maximum current here, and this is the characteristics what you get here. Okay. And if you draw a rectangle out of this point here, and this will have a coordinate of ISC into VOC. This is nothing but a power, okay, maximum power what you can extract from this. Okay. And now, solar cell, where do you operate solar cell to obtain the maximum? Because you cannot operate at this voltage here, because that is very difficult here. And if you observe the characteristics here, if I choose a point here and observe the region under this the curve here. So, this region, if I shade it let me shade it in different color, this region you can see here, this is very small. So, the V into I, whatever you choose here, this is a V, and if I choose as a I1 here, so that area and coverage is going to be very less. And if I choose another point, say here, you can see here again this is better compared to the this region whatever you have chosen here. Let us say this is region 1 and this is region 2. Region 2, you can see this is the voltage and this is going to be the current. Comparatively, this area is going to be larger within this characteristics compared to this region R1 here. So, therefore, you have to find optimal point here where you get maximum area within this the curve, within this the characteristics here. Let us assume that PM is going to be the maximum the area, okay, for some value of voltage and some value of current here. Let us call that as Vm into Im here. Let us call this as Vm here and this value as Im here. Some point you will get maximum area of within this the characteristics here. So, that point let me call as Vm into Im here. And now, we are going to define what is called as a fill factor, which is an important formula for solar cell. Fill factor is nothing but which is Vm Im, this is nothing but Pm, which is equal to Vm times Im. So, this is nothing but this I2 now we can call as Im, and this corresponding voltage is let me call as Vm. Vm into Im, that is called as a Pm. So, now if you take a ratio of this area to this bigger rectangle square area, the ratio of this to this is called as the fill factor. So, this is nothing but Pm, P max whatever you get it here Vm into Im to that of VOC into ISC, this bigger rectangular area, the ratio of this gives you the fill factor. Since this denominator is going to be always a large value compared to numerator is a subset of this the VOC into ISC. Another way I can say that this bigger square, okay, whatever you are observing, and area what you choose to harness maximum solar energy, this area over this area is always less than 1. Okay. So, if you maximize this area equal to 1, then you are going to extract maximum energy from the solar cell here. Otherwise, the energy extracted from this solar cell will be less. So, it is left to you now which point you choose in such a way that you obtain maximum region in the within this characteristics here. Okay. So, this fill factor is very important formula for solar cells. Now, let us see the formula for conversion efficiency. So, conversion efficiency is eta, what we say, is given by Vm into Im divided by P in. So, P in is nothing but it is an incident power here. So, incident power, okay, Vm into Im is nothing but it is a maximum energy extracted or maximum power delivered by the solar cell is Vm into Im, and Pn is nothing but incident power here. We can also substitute this Vm into Im in terms of the fill factor. We already know that fill factor Ff is nothing but Ff into this VOC into ISC gives you the Vm into Im. So, if you substitute this Vm into Im as fill factor times VOC into ISC, we get another formula for conversion efficiency. So, therefore, the final formula for conversion efficiency is fill factor times VOC into ISC divided by incident power, which is nothing but power due to the incident photons here. So, this is about solar cells. I think we have covered most of the things related to the solar cell, and if you have any questions I can take it before we move on to the other topics.